So on page 508, and it's number 20. It's x cubed minus 13x minus 9. Now here the denominator is lower degree than the numerator. So what you have to do is, first of all, just divide it out in long division. So what I'm going to do is I'm just going to go and this is going to be x. So that's x cubed minus, oh, I didn't leave enough. Didn't leave myself enough room here. It's actually 0x squared minus 13x minus 9. So then I have x cubed, then minus x squared minus 12x. And then we change the signs. Negative, plus, plus. And then we get an x squared minus x minus 9. And then you take this into here, and that's going to be plus 1. And then we can have x squared minus x and minus 12. And you change your signs. And then you have, oh, I didn't change that sign, 3. And then you have a plus 3 over this thing remainder. And then you do the partial fractions on that thing. So your answer is going to be x plus 1. And then it's going to be the partial fractions of this. Squared minus x minus 12. Now that's 3, and then the factor here is 4 and 3, right? X minus 4 and x plus 3. So dividing into partial fractions, it's a over x minus 4 plus b over x plus 3. And then this and this, you're going to clear the denominator. So you're going to multiply this by x minus 4, x plus 3. And then you're going to multiply this whole thing by so then you have 3 equals a. When you multiply this times this, you're just left with x plus 3. And then it's plus b, and the 3x plus 3's go out, so it's x minus 4. So then 3 equals, and distributing the a, ax plus 3a plus bx minus 4b. Then you combine like, or you join the like terms there. Ax plus b x, and it's plus 3a minus 4b. And you factor the x out, so it's a plus b x, and then this is the constant term, 3a minus 4b, and this side is 3. Now really what there is on the left hand side is there's a 0 times x plus 3, right? And that means that a plus b equals 0. And then 3a minus 4b minus 4b has to equal that 3. Okay, are you good with that? And then you're just going to have to use this and eliminate one of those, and I guess I could multiply this one by plus 4. So I get 4a plus 4b equals 0. Then just bring this on over. 3a minus 4b equals 3. Combine them and I have 7a equals 3. So this goes out, right? A equals 3 sevenths. Then I can substitute this back into a plus b. Oops. A is going to be 3 sevenths plus b equals 0, so b is a minus 3 sevenths. And what I've done, it's this thing right here, plus a over x minus 4 plus b over x plus 3. Remember to put that, got to put it down here so I can x plus 1, right? Plus a over x minus 4 plus b over x plus 3. And the a is 3 sevenths. X minus 4 plus minus 3 sevenths. X plus 3. And if you wanted to put this 7 down and multiply it through, you could put 3 over 7x minus 28. Yeah. And that would be 3 sevenths times this, so it would be 7x minus 28 minus 3 over 7x plus 21. I guess that'd be it. Any questions on that one? Everyone's good. You see, everyone's okay with where I went here, right? Okay, no problem. I can do one more. 30. 3x2. How about 2? 2x cubed plus 9x plus 1. This is x to the 4th plus 14x squared plus 49. Now that denominator is actually factors into x squared plus 7 the quantity squared, right? And that's as far as it'll go down. So now if you did partial fractions, you'd have to put ax plus b over x squared plus 7 plus, I think this is the breakdown, ax cx plus d over x squared plus 7 quantity squared. I think that's case. It'd be like case 4. Whenever you have a second degree polynomial squared in the denominator, then you break it down that way. And then you have to multiply both sides by x squared plus 7 squared to clear the denominator. X squared plus 7 quantity squared. So on this side, it's the numerator is just 2x cubed, and I'm going to put in here plus 0x squared plus 9x plus 1. And then when I multiply this times this is ax plus b times x squared plus 7, because one of those x squared plus 7's goes out. Then it's plus cx plus d. And this thing here, I got to FOIL it. So it's going to be ax cubed. I'm just going to run this ax through here. Plus 7ax. And run the b through there. It's b x squared plus 7b. And it's plus cx plus d. Now I'm going to get everything with cubes. It's only the ax cubed. Then I'm going to get the squares, and that's only the bx squared. And everything with x, it's plus 7ax plus cx. This one and this one. And the constants are plus 7b plus d. And the only thing that I got to do here is do this one, take the x out. So this plus 7a plus cx. Then this is a group, 7b plus d. Now did I do all my grouping and everything right? This is 2x cubed plus 0x squared plus 9x plus 1. So that makes a equals the 2, right? And then b equals the 0, because it's the only thing in front of us squared. And then 7a plus c equals 9, and then 7b plus d equals the 1. So I have a and b. I can get c by plugging a into this one, right? So I would go 7 times 2 plus c equals 9. So c is going to equal 14 goes over here negative, so it's a negative 5. So it's A equals 2, B equals 0, C equals 5, and then I do B is 0, so D is 1. Oh, that thing right there. I need to have that. I'll just, so it's 2x cubed plus 9x plus 1 over the x4 plus 14x squared plus 49. And I'm going to write that out. It was ax plus b over x squared plus 7. And then it was cx plus d over x squared plus 7, the quantity squared. So this was going to be 2x plus, well, that's just 2x over x squared plus 7. C was 5 minus 5x plus 1 over x squared plus 7 quantity squared. And that was what this was equal to. This is its partial fractions. That would be breaking it down into its partial fractions. Okay. They're not too hard, not nearly as hard as that section 6.3. Do you have any questions on anything? I think it's 6.4. And what we're going to do is we're going to jump to 8. And that was 6.4, right? Oh, 6.4. I'm not sure that I can get 6.5 done. 6.5 is really a precursor if you ever go into, it's linear programming, and it's when you do inequalities in second degree polynomials, or that's the precursor of doing that. And linear programming started in World War II when were trying to figure out transportation problems. If they had depots in different places and they were trying to move equipment to certain places, it would be they set up their linear restrictions and then they have maximization functions. And that's where it came from. And then it developed into it. It's used logistically whenever companies are, have warehouses and they're trying to move things around and to figure out what's the best way to move it and what's the least cost operation. So I'm not going to do it, but it's all simultaneous solutions of linear equations and getting a region, a constraint region. I think that if you were trying to had to do it with a little bit of training, you could understand what it is from what we have done so far. And then section 7 is solving simultaneous equations using matrices and determinants. So it's just linear equations, but it's using the process of matrices and determinants, and that turns out to be, in the end, solving it, especially with the advent of the calculator. It becomes a pretty simple process. It used to be really hard because they used what they called the Gauss-Jordan elimination method to solve it. But it's once again when you can use a calculator like the graphing calculator, it becomes a pretty simple problem. So what I'm going to do is sequence in series, and we have to get through 1, 2, and 3 for sure, and so that's why I'm electing to take, what do I have? I have 3 plus whatever time here, 3 periods plus this time to get through 3 sections. I just want to make sure I had time to get through it. So we are on 602 on page, no, we're on section 8.1. And it's infinite sequences and summation notation. So a sequence is just a list of numbers, but order makes a difference. So, and they're telling you there in the top of page 601, you can have numbers 2, 4, 8, 16, and 32, but if you change it around to 2, 8, 4, 16, 32, that's a different sequence, and that order is important. So its order is important. And now, although it is a function, usually our notation is that the first element in a sequence is listed as A1. So if you took that sequence 2, 8, 4, 16, 32, and the 3 little dots mean however that sequence was in that, it continues in that respect. So A sub 1 would be 2. This is the domain, and this is the range values. These are range values. So A2 is 8, A3 is 4, A5 is 16, A6 would be 32. And this designates the different elements in the sequence, and it'll usually go 1, it'll usually be a positive integer. Sometimes in some sequences they will start with the first one being 0. Most of the time it's 1, it's the positive integers. So it's a mapping of the positive integers onto the elements of the sequence. Rather than saying f of 1 equals 2, you would say a sub 1. So you could say f of 2 is 8, and so on. It's a functional notation. Because for every x, there's one y. But this is the typical way to use it. And they're saying an infinite sequence in that box is a function whose domain is the positive integers, that is, these are the positive integers, and whose range is a set of real numbers. So it's any real numbers can be represented out here. And then they're telling you that occasionally you will include 0. The first one will be 0 rather than 1. If it works out that it's easier to represent it that way. Now, an alternating sequence. If I wanted to take this same sequence and have it look like this, that this was positive 2, then this was negative 8, and then 4 and negative 16, and then 32 and the next one negative. That would be alternating. It's alternating in sign. That's what alternating. And then what I would do is I would say A1 equals, now this sequence you would try to represent it some way. I should let me get a new one that I can represent. If I say a sequence AN is 2n, so then A1 would be 2, right? A2 would be 4, A3 would be 6, A4 would be 8, and then so on, right? This is my general term. Now, if I wanted to alternate that sequence, this is what I'd do. I'd say A, and if I wanted it to be 2 minus 4, 6 minus 8, then the general form I would do is AN is going to be a negative 1 to the n plus 1 times 2n. So then to get this value, if I use this representation, A1 would be a minus 1, 1 plus 1 to the 2 times 1. And you see that would be 2, right? Then this would be A sub 2 would equal a negative 1 to the 2 plus 1, 2 times 2. Now 2 plus 1 is 3, and the power of 3, negative 1 to the power of 3 is a negative. So that's how you would get an alternating sequence. You would make it so that the power was even and odd of 1 raised to that power, minus 1 to that power. And then if you did it right, then you could get your sequence fit right. Does that make sense? And that's the way you do it. You just make minus 1, and then you just make your powers. You write your exponent in such a way so that when you substitute your domain value in, you get the proper sign that you want. Okay, a recursively defined sequence. Recursively defined would be, usually you have to have some of the first elements of a sequence given to you. This would be a pretty simple one. If I define the general element of the sequence after the second element as AN was AN minus 1 plus AN minus 2, and I'm giving you the first 2 so that when you go to evaluating A3, this was 2. When you do A3, you take the previous one, 2, and add the other one, previous. So this is going to be 3. And then A4 is going to be 3 plus 2. And A5 is going to be 5 plus 3. That's recursively defined. It's defined in something, an element previous to it. So usually you have to be given, like in this kind of recursively defined sequence, you have to have the first two given to you. You can't do it. You can't just do the general element of the sequence. Something has to be given to you. And there's lots of ways you can recursively define them. But that's what the terminology means. Now there's a factorial that they're talking about on 6.4. And if they do something in factorial, well, for example, if I would do 4 factorial, what this means is I take 4 times 3 times 2 times 1. If I go 8 factorial, it means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now here's a trick that you want to remember is if you have 8 factorial divided by 4 factorial, you see you can write this numerator as 8 times 7 times 6 times 5 times 4 factorial over 4 factorial, and those will cancel. That's the kind of stuff, that's the way you want to work with factorials. Because you can have something that looks just horrendous, but if you realize that any factorials, and then use the largest factorial that you can get out of numerator and denominator. Now, in this process, 0 factorial is always defined to be 1. When you factorialize 0, it's always 1. And this, what I'm showing you here, is they're just showing you that if you go n factorial, you can say n times n minus 1 factorial. So if you had n factorial over n minus 1 factorial, you just have n, right? Okay. When you do, next thing is going to be partial sums and summation notation. Now, these are sequences back here, but you can sum sequence. You see, if I sum the first 3 terms of this sequence, then what I would write is I'd write the summation of I equals 1 to 3 of a n. And that would tell you that what you're going to do is you're going to sum a1 plus a2 plus a3. So you're going to sum 2 plus 4 plus 6. And then you're going to get 12. That's a partial sum. And this is a summation notation. This tells you where you start, this tells you where you end. And that one's called a partial sum. Okay. Now, when you're doing summation notation, notice there on the bottom of page 605, they're saying number 1, if you have the sum of I equals 1 to n, and you have ai, and they're saying plus or minus, I'm just going to go plus bi, because it's ai plus or minus bi. What you can write this as is, you can write this as a sum of I equals 1 to n of ai plus the summation of I equals 1 to n of bi. And if you can just change this to a negative, and this goes negative, right? So that's, then they're telling you the second thing is that if you have the summation of I equals 1 to n of C A I, then what you do is you take that C out in front. This is a constant. Summation of I equals 1 to n of A. I'll just take an example to show you why it's this way, because that's just a common factor. You see, if I had the summation of I equals 1 to 3 of C A I, and if I wrote that out, I'd have C A1 plus C A2 plus C A3. I could take that common C out, and then I could do A1 plus A2 plus A3, but that is just C summation of I equals 1 to 3 of AI. You see, I mean, that's all that that's saying. This is a constant times an element, and it just has a common factor. So that's why it comes out. And then the third thing is if you sum, and they're saying I equals 1 to n of C, then it's just n times C. Because what that is, an example of that is if you did the summation of I equals 1 to 3 of C, then what you would do is you would go equals C plus C plus C, which is 3C. If you did it more specifically, if you did the summation I equals 1 to 3 of 4, that would be 4 plus 4 plus 4, which equals 3 times 4. So what you can do is when you have these different situations, have something looks like this or something looks like this, you can write it like this other side. And sometimes that'll help you solve it. That's all it's telling you about. All right, any questions on? All right. 606, then we'll do some problems. Number 6. 6 is saying it's defining an to be a minus 1 to the n plus 1 over n times n plus 1. And now it says find the first 3 terms and the 8th term. So A1 is going to be a minus 1, 1 plus 1 over 1 plus 1 times 1 plus 1. So what you have is you have a positive 1 in the numerator, 1 times 2, 2. That's the first term. A2 is going to be a minus 1 to the 2 plus 1 over 2, 2 plus 1. So this is a negative 1 in the numerator. And then this is 2 times 3, negative 1/6. And then A3 is going to be a minus 1 to the 3 plus 1 over 3 times 3 plus 1. This is going to be a minus 1 over 3 times 4, so that is a minus 1/12. So here's your first three terms. I think this is plus, because it's an alternating sequence I have before. So that's all you do with those. Pretty simple, right? Okay. I don't know. You want to look at any other ones 1 through 24. I think they're pretty straightforward. 25 through 34 is recursively defining them. What I'm going to do is, and you'll notice that when they recursively define it, they will have to give you the number of terms, the first terms of what the recursiveness is. If they're recursively defining it in terms of one previous one, they have to give you the first one. If it's two previous ones, they have to give you the first two elements. You got to know the first two. If it's three, then obviously you have to have the first three. I'm going to go over to 35 and 36. Those are a little bit harder. And it says find A3, A4, and A5. 36 is given you. Notice A3, A4, A5, it's defined in terms of the previous two. So they have to give you A1 is 1, and they have to give you A2, which is 4. And then they're defining the general term AN as AN minus 1 times AN minus 2. So then A3 is going to be 4 times 1, which is 4. A4 is 4 times 4, 16, and A5 is 16 times 4 is 64. So here's the ones that they want you to calculate. Once again, I don't think they're. Any questions on that? (39 through 46). I'll do 46. It says 100 factorial over 98 factorial 2 factorial. Now, this one, the easy way to do this is do 100 times 99 times 98 factorial. 98 factorial times 2 factorial is actually just 2 times 1, right? This goes out with that. 2 goes into here, 50, and then 50 times 99. If I multiplied right, that's the answer, right? So always cancel out, and always can't. You could have did the 2 factorial, but that would have screwed you up, right? You'd have to go to 100 all the way down to 3, and then done 2 factorial and cancel the 2, but then it messed you up with this one. So in the denominator, take the highest factorial and take it into the highest in the numerator, and then that will make it become as easy as possible. And that's really all those are about. Now notice the problem 39, it says 7 factorial minus 6 factorial. There's nothing you can cancel, because those things, you cannot subtract factorials. I'll just have you look at 39. 7 factorial minus 6 factorial. 7 factorial over 6 factorial. You see this thing here, you actually have to do 7 times 6 times 5 times 4 times 3 times 2 times 1 minus 6 times 5 times 4 times 3 times 2 times 1. You can't take this part of that off of there. It's not right. You could factor 6 times 5. You could actually do this. 7 minus 1 times 6 times 5 times 4 times 3 times 2 times 1. And then take 6 times that. That would be possible. Because the reason that you can't take it off, because this thing is 7 factorial over 6 factorial is 7 times 6 factorial over 6 factorial, and that is 7. Don't try to make this thing 7. It's not 7. This is 7. See what I'm telling you? The best you could do is take the common factor out of the 6 factorial out of the 2. Then you'd have 7 minus 1 times 6 factorial. That's a big number. But this thing is only 7. If you don't understand the difference, you better look at it and figure out the difference between the two. Huh? The answer to this one is 7. The answer to this one is this right here. And that's, I don't know, I'm not going to multiply it out. I can tell you the answer. This is 4,320. And what you'll try and do is you'll try to make this one 7, not this. That'll be the typical error. That's why they put that one problem in it. They didn't put anything else. Everything else is. Okay, now come the ones that are a little bit harder. Let's do 50. It says evaluate the series. Here they're saying the summation of I equals 1 to 7 of 2i plus 1. Well, you either got the choice of doing it this way. 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1, and keep doing that. Or else you write this way. 2i plus summation of I equals 1 to 7 of 1. Then applying your rules, this thing comes out in front, and it's summation I equals 1 to 7 of I plus, and what's this? 7 times 1, right? That's what the rule says. So now then you'll take 2, and then you do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 7. So then you can, this is a little bit easier to calculate out. 3, 6, 10, 15, 21, 28. 2 times 28. I don't know, make sure I added right. So this is 56 plus 7, so that's 63. Right here, summation? Well, this is a 2. I was leaning on my keyboard. I took that 2 out. That's using that rule in that on page 605, number 2. rule? A constant times (54) summation I equals 1 to 6. This is 2I plus 1, 2I minus 1. Now, one way you can do this is you can go 2 times 1 plus 1 times 2 times 1 minus 1. That's the first term. Plus 2 times 2 plus 1 times 2 times 2 minus 1. You can keep doing that for 6 of them, right? What's another way you can do that? What about foiling that? What happens if you foil that thing? This becomes summation I equals 1 to 6. What's this foiled? 4I squared minus 1. It's 2I plus 1, 2I minus 1. It's the first term squared minus the second term squared, isn't it right? Now, what does your rule say you can do with this? You can bring the 4 out on the first term, summation of I equals 1. Well, let's just do it step by step. The first rule says that you can take this and write it as the summation I equals 1 to 6 of 4I squared minus the summation of I equals 1 to 6 of 1, right? That's that back there, that rule number 1, right? Now then, Rebecca, you can take the 4 out, right? You can take 4 summation I equals 1 to 6 of I squared minus, now what is this going to be? What's rule 3 say? That's a constant 1. It's 6, isn't it? 6 times that 1. This is just 6. See, if you go back and look at that on 605, number 3, says if you got a constant, then what it is, it's this constant times that power right up there, that one right there. So that'd just be 6 times 1, right? Now there's nothing you can do with this I squared, but that's a little bit easier to evaluate than doing all this, right? So what am I going to do here? I'm going to go 4, and then it's going to be times the sum. So what's the first term going to be? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and then minus 6. Now, that's easier to evaluate, right? 1 plus 4 plus 9 plus 16 plus 25 plus 36. And then you have to remember you have to multiply 4 times and subtract that 6. I think I can even almost do this in my head. There's 14, that's 30, isn't it? 45, that'd be 51, and 3 is 81. Did I do that right? So it's 4, 3, 2, minus 6, 3, 1, 8. Is that right? This is what? This is 91? Okay, I'll buy it. I was doing it in my head. Wasn't so good. Then this is 436, right? And then it's 358. Is Is that what you come up with? Okay. But you see, when you, the point is this, you can calculate it out this way. But that's just pretty, it inclined to more mistakes than what I make. Okay. So let's look at 58. Says the summation of n equals 2. Now notice that don't have to go clear to start at 1. ln of n over n plus 1. All right. Now, what you can do with this thing is you could just list it out. You could go ln of 2 over 3. That's the first one, right? 2 over 2 plus 1. Then you go ln of 3 over 4, and then you just keep going that way, right? But here's another thing that you could do. You could do the summation n equals 2 to 8. ln of a quotient is what? Difference of ln's. ln of n minus ln of n plus 1. Is that right? All right. Then what does my first rule say? I can do the sum of each one of those. Now this one, if I start listing it out, this one is going to be ln of 2 plus ln of 3. It's going to go on and on until you get to the ln of 8, right? And this is ln of 3 plus ln of 4 plus, and it goes on and on until you get to ln of 9. These are all negatives, right? Do you see what's going to happen? In this one, everything from ln3 has got a negative ln3 over there, all the way out to 8, right? The only ones that are going to be left is ln2 and an ln9, right? So this is going to be ln2 minus ln9. A little bit simpler, right? If we understand our different applications. And then this ln2, this just plug it into the calculator, right? But you don't have to put all of this stuff in, and you don't have to put it in this way. It's not to say that this you couldn't calculate it, but, or you could do this and then recognize that this one is ln2 minus ln3, and then this is ln3 minus ln4, and then see that you're canceling everything all along until you get to the last one. All right, so I want to look at the next one. Says write the given series in summation notation. Now these thinking things are hard. At least I find them hard. 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14. And what you want to do is write it in summation notation. 1, 2, 3, 4, 5, 6, 7. So this would be I equals 1 to 7 would be one possible way to do it. Now then, how are you going to represent 2, 4, 6, 8, 10, 12, 14? No, here's one way of doing it. 2 times I, wouldn't it be? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5, 2 times so on. You try to look for how to represent it in this manner. Look at 61. See what it 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36. Summation of I equals 1, 2, 3, 4, 5, 6, right? What are you going to do? The denominator is the square of these numbers. So you'd go 1 over I squared, wouldn't you? Correct? Because the first one would be 1 over 1, 2 squared is 4, 3 squared is 9. So that's that one. 63. 2 minus 4 plus 8 minus 16 plus 32 minus 64 plus 128. 1, 2, 3, 4, 5, 6, 7. So what are you going to do? It's an alternating one, right? So what does that tell you? You're going to have to go minus 1. Now the first one is positive, so what would you have to do? You'd have to go I plus 1, right? Because 1 plus 1 would be 2, and negative 1 to the second would be squared. That would give you positive, right? Now how are you getting 2, 4, 6, 8? 2, 4, 8, 16, 32, 64. Would that do it? I plus 1 squared. When it's 1, this is 2. No. Maybe you'd go 2. That ain't going to do it, is it? So what's going to do it? What's going to get a sequence? 2, 4, 8, 16. Okay, so when I is 1, it'd be 2. When I is 2, it's 4. When I is 3, it's... that doesn't fit. I'm giving you an opportunity. These are hard. I find them really difficult. Anyone got an idea? Let's see, each one of these things is, this is 2 times the previous one, isn't it? This one's 2 times that, that's 2 times that, that's 2 times that, that's 2 times that, isn't it right? What's that? You mean this thing right here? So I'm getting these signs right here, right? Plus, minus, plus, minus. But now how do I get the 2, 4, 8, 16, 32, and so on? Okay. But does just 2i work? 2 is 1, it's 2, right? If 2 is 2, it's 4. No, that don't work. It's 2 times the previous, right? All right. I'm not seeing it. It's 2 to the power I. Is that what you said, Zach? Yeah. It's 2 to the power. 2 to the power. So 2 to the first is 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. All right. I was trying to do it without looking because these are really hard for me. I just never have good luck with it. But you're going to have to do them. Let's look at 66. It's 30 plus 26 plus 22 plus 18 plus 14 plus 10. So we got 1, 2, 3, 4, 5, 6. Summation I equals 1 to 6. What do you think? You're saying I minus 4? How does that make the first one? 1 minus 4? Don't work. You see, like the difference here is 4. Difference here is 4, isn't it? All 4s. So what would happen if we start out with 30 and subtracted 4 times I minus 1? Then the first one would be 30 minus 4 times 1 minus 1 is 0. That'd be 30, right? Then the second one would be 30 minus 4 times 2 minus 1. That would be 4. That would get us there, right? The next one would be 3 That'd give us that, wouldn't it? And if we simplified this, this would be 30 minus 4i plus 4, right? So we could call it 34 minus 4i, summation I equals 1 to 6. And 1 would be 30, 2 would be 8 times, find away from that, and so on. I mean, there's several ways you could do it. The minus 4 was right. It's just how do you figure out the first thing. This here's the book answer. You see, they started out at 0. And they only have 5 because see, there's 6 elements, but if you start at 0, you got 6 from 0 to 5, right? Correct? If you go 1, 2, 3, 4, 5, you got 5. You go 0, 1, 2, 3, you go 0, 1, 2, 3, 4. Where am I at? 5, you get 6. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. I knew it was 5, so I knew it was 1 less. So what about 67? How are you going to do that one? So there's what you should be able to see is there's lots of different ways that you can lay these things out. Here we got 1/2 plus 1/4 plus 1/8 plus 1/60. Summation of I equals 1. We got 4 of them, right? What are you going to do with that? 1, 2i. But the only thing is, what happens when you get to the third one? Or if you did I in the numerator, the second one would have to be 1, right? What would happen if you did it this way? Two to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, right? 1 over 2i, 2 to the i's power. That's it. That's one way. All right, I've used the time up. Unfortunately, I got it made out, but I don't have it run off this section. I don't have it. These things are hard, but they're important. Important. Yeah. I suppose those are $50 units too.
They are. Well, I didn't pay $50.
Eric, would you pay $50 for those jeans?
Well, good, because they're girl pants.
You wouldn't pay $50 for your girlfriend or wife, would you, for those jeans?
Yeah, but see, they're $50, but I only pay like 15 or
Well, I don't, would you pay 50 or 20 for it? Sure. You just don't want to attend it.
It's okay.
I did.
Oh.
I know you guys well enough, I can remember. Yours is a six.
Can I get 5-3 from you? Do you have it on you?
Yeah.
I realized when I was doing homework the other day, didn't have that. 'Cause we only did what?
5-3? I don't have 5.
No, yeah.
I got, did you get 6-4?
I got 6-4.
Did you get all the sixes?
Because we did what, 5-1, 5-2, and 5-3.
Yeah, we did, everything's 5.
All of 5.
1, 2, 3, 4, 5. We did through 6, I think 5, 6. I don't know where we did all of them.
Mr. Stephen, there's 6-3, 6-4, and chapter 5 word problems. And then I only have a couple more to do on chapter 5.
Okay.
Is it okay if I turn
Yeah.
it to you Wednesday? What are you gonna hand out Wednesday too?
Well, I'm gonna hand out 8-1, probably 1, 2, 8-2.
Can I have both of those then?
But I don't have a runoff. I got it paid out. So I don't have, I have run them through the printer and
Okay.
printed them. I only have the original copy.
Should I go with you real quick to do that?
Yeah.
So I can get those? Cause you handed out today 6.4, right? That's the only thing.
6.4.
That's it?
And then I just hand it to you.
Just go through this.
Or Mr. Stephen, do you have it saved? You could just